My name is Jonathan, and I do computational space physics research and calculate a self-consistent equilibrium in the Earth's Magnetotail current sheet. Now, the Sun is continuously sending radiation out to the Earth. The Earth is protected by the Sun's solar radiation by its magnetic field. The solar radiation colliding with the magnetic field causes the field in front of the Earth to be squished and the field behind the Earth to be stretched out. This is called the magnetic tail. Now, my research is concerned with conditions of the current sheet in the magnetotail that we saw in something called a magnetic substorm. A magnetic substorm occurs where the magnetotail is stretched so far out that it snaps, sending particles both away from and towards the Earth. These particles will collide in the polar regions of the Earth. We can see this from space as they collide near the auroras. Now, we are concerned with this because it can cause telecommunication issues, endanger astronauts, amongst other problems. Cold reweight depends on a couple general considerations: that the magnetic field varies from positive and negative constant, that if the magnetic field is zero in the z direction, that the orbits are nonlinear, that current is caused by particles streaming through the current sheet, and that diamagnetism leads to a decreased field amplitude. Our computation takes this form. We assume some initial magnetic field. We then launch a Maxwellian drift distribution of particles into the current sheet. We push them through the current sheet and we calculate the pressure, the temperature, and other current they contribute to the current sheet. We then use the results at the end to calculate a new magnetic field. We compare the two magnetic fields together, create a new magnetic field, and we redo the calculation until it becomes self-consistent, which occurs roughly after 100 iterations. Now, our code depends on several equations, the most important of which are a magnetic field model and a Boltzmann pressure balance. Now, we can get results from this computation, such as for an equilibrium for BC equal to 0.1 and E drift of 0.025, the thermal energy with a particle density of half a particle per centimeter cube and an initial B strength of 15 nanoteslas. We get a nicely realignment of the magnetic field. We get a smoothly peaking current density in the midplane. We get a peak in the particle density, but not as strong, and the pressure remains relatively constant. Now, if we do results for a zero mass electrons at varying drift velocities, we get when the drift energy is higher, that the particle density is higher at the midplane. The same thing occurs for the current densities, and we still get smoothly varying magnetic fields. We also find that as the drift velocity increases relative to the thermal energy, that the current sheet thickness decreases. This is important because thinner current sheets result in more likely of a tearing of the magnetic field, resulting in magnetic substorms. In conclusion, we have a code that successfully calculates self-consistent magnetic fields. Our code convergence after approximately 100 iterations. The smaller the drift velocity, the longer it takes to converge, and there's a minimum required drift velocity for this to happen. The field line as an asymptotic distribution creates a thinner current sheets with peak particle densities and lower pressures than more uniform distributions, and our results are consistent with previous models and experimental measurements. Our future work including a more sophisticated electric model, so we can include electric fields, and we want to do a PIC simulation to simulate equilibrium.